Hello, this is Michael Yeager. This is a short 5-minute or less video to help you clear up any muddy points that you may have following Josh Black's GeneExpression123 lectures. This is not designed to replace Dr. Black's lectures. Please review his learning objectives, the PowerPoint slides, his lecture notes, and if after that you need to review his lecture session by watching Panopto, please do that. If after that you still have muddy points, I believe this video that we've made quickly, low production value, but should help you very much to get through some of the stickier points of that lecture. In this lecture, we're going to talk about this two-component system, DNA proteins. We're also going to do a little bit of order of operations. How do we get this party started? And then finally, we'll wrap up with how do we control this. So if we've drawn DNA properly, this is a little bit messy, but I think what you can see is by virtue of the ATGC sequences, and not that particular sequence, just the nucleotide sequence, an emergent property arises, and that is that DNA has a surface topology. If you look at a barber pole, this barber pole is interesting because the distances between the blue and the red stripes, for example, is not the same. So we have a minor groove and a major groove that go along the topology of this DNA, and that's very important because transcription factors, those things, those proteins, which bind DNA, do so by virtue of interactions, non-covalent interactions, based on shape largely and charge, and they intercalate into these minor and major grooves, almost like fingers in a glove, let's say. And that gives you some idea of, if you have a question in your mind about, hey, how do these transcription factors know where to go on DNA? It's complex, but part of that answer is that they fit in minor and major grooves. And some transcription factors are minor groove binders, some are major, and some have both. And sometimes they bind as dimers, which give them an overall structure which can bind minor and or major grooves. Okay? Now, these sequences, places like this, and promoter elements, let's have a promoter element right here, right next to this transcription start site. These are like H paints on helipads. It indicates where that pilot should put the helicopter down and land. So these are TADAs, proximals, enhancers, and insulators, all those anatomy elements of DNA control of initiation that Dr. Black went through. Please remember, too, that the distance along DNA is really irrelevant. We can have HMG and other DNA bending proteins bind way, this could be millions of bases upstream from this, and simply that this will bend and bring this enhancer element, which is way upstream, to bear on affecting local gene transcription. So we have proximal or local elements, and we have very distal elements as well. All right, let's get to the proteins. So here's some transcription factor anatomy quickly. This transcription factor, here's the N terminus and the C terminus. This transcription factor has several domains on it. Here's a DNA binding domain. We should put a little B there. Binding domain. And this is the place that's going to make direct contact with the DNA. And this tells you a little bit now about, okay, what is a transcription factor or what's an activator, coactivator? This was a little bit confusing. So let's unconfuse. A transcription factor, also sometimes called an activator, has a DNA binding domain. If you are a co-activator or a co-repressor, you're involved in the party here, but you are not directly contacting DNA. Let's take a look at this. This transcription factor has a DNA binding domain, and let's just say it has an ATPase domain as well. And let's say it has two protein-protein interaction domains where it can involve itself in complexes with other proteins. And let's say it's got an HDAC domain, an histone deacetylase domain. That'll be interesting later. And let's suppose this transcription factor is in the nucleus, that's where we are, and binds DNA. Let's call that then a general transcription factor, and it binds this promoter. And let's say that that causes recruitment versus via this protein-protein interaction domain, recruitment of other transcription factors and even coactivators. These are coactivators as drawn because they are not making direct contact with the DNA. Okay? And it's this collection of players here that can give us combinatorial control and either turn on or off this gene. So let's look at the order of operations and talk about combinatorial control. And so if we go back quickly, if we go back here, one of the things we need to do is get access here. Just binding here is insufficient to drive transcription. If we bind a major minor groove right here at this promoter, that's still insufficient. We've got to open up the DNA, and we do that by helicase activity by virtue of this ATPase domain, and we get the DNA open. And I'll show you that right here. So to get this party started, we know that DNA exists as either heterochromatin, which is more compact, or euchromatin, which is more open. When these transcription factors bind, so here I'm going to produce a transcription factor. This transcription factor, as we know, starts off like any other protein. It's first made as mRNA. That mRNA is taken out of the nucleus and at the ribosome is translated into our friend from the last slide with all of its very good domains. This protein is now brought back into the nucleus and finds its promoter element, builds our party like in the last slide. Again, same with this coactivator. This one has to be made as an mRNA. At the ribosome, we are making now, by translation, this protein. And this coactivator comes down here and joins the party as well. And we've got our situation from last time. In this case, though, there is a conversion thanks to this transcription factor and its ATPase domain that we open the chromatin. And this can be by either DNA methylation or histone acetylation and methylation. But in any case, the combination of transcription factors and all these cofactors binding here opens up this DNA for business, and we get a transcription bubble, which we can see here, where we've opened up this DNA and now we've got something going on. Now, how about combinatorial control? This is a little bit muddy in the lecture. Let's clear this up. Combinatorial control refers to who is there, that's what that says, and where is there. So the combination of the production of these factors and their ability to make a complex here is combinatorial control. So who is there? It depends on what factors are here. If on the same promoter you change the combination of transcription factors, coactivators, co-repressors, whatever, you will get a different result than a different combination. Okay? So that's who is there. Where is there? Some of these general transcription factors can bind lots of other places, and some of the gene-specific transcription factors can turn on some genes and turn off others. So a very complex regulatory situation. Now, how do we control this? We control in three ways. Access. If these transcription factors cannot get back in the nucleus, if we close this door, think of this as the bouncer at a bar. Maybe he or she will not let these players back in here. So access becomes important. So here I put N and B. So nuclear access. Am I getting in here? Access also means, can I get with my team here? Can I be in the right place? Status, post-translational modification. If we modify this with phosphorylations or other kinds of post-translational modifications, does it go in the nucleus, or is it now prevented from being in the nucleus? Or perhaps once I'm in here, my post-translational modification status changes my ability to interact with these players. Remember, when we get a post-translational modification, say here, it might change this domain shape. It might make it unavailable now to perform an ATPase function. Or if it's over here, maybe I can't interact with some of these other players, or maybe now I do interact with different players. So we can fine-tune that response as well. And finally, it's about concentration. If you can't get a lot of these factors or a sufficient number into this nucleus, it's going to change the overall output of gene expression. Concentration is also not just de novo factors that are made as I indicated, but also perhaps we can control overall expression by sending some of these to the proteasome where they're degraded into amino acids. So controlling the concentration, the production, and the degradation, along with access and status, is really about what you need to know for combinatorial control. Finally, I'm a lung person, and so a really smart person who trained me told me to think about gene expression. So here's a piece of DNA, here's a piece of DNA, and here's one, and here's one. To think about it from a lung scientist perspective. So if we looked at gene transcription from 30,000 feet, we would see transcription bubbles opening and then closing. And maybe this one opens and then closes. And same here, same here, same here, and same here. So if I did a movie with this little video presentation, you would see this one opening and closing, and this one transitioning from opening and closing, same. And so the DNA all over is breathing. And I think that's a very, very nice way to think about gene transcription. If you were to have your bionic eyes and look at your patients down at that cell molecular level, you would see patterns of DNA being transcribed and then not being transcribed, and it would look like breathing. So I hope this video has helped, and I look forward to perhaps making some more. Enjoy.